Hi again, friends. So in chapter 12.3, we are talking about the second and third laws of thermodynamics, and we're also going to do a slight amount of math. I know, not a fan of math, but hopefully it will help. So, due to the fact that matter and energy cannot be created nor destroyed, we have the entropy of the universe is equal to the entropy of the system plus the entropy of the surroundings. So if we take the whole thing as our universe, we have our system, which is generally our reaction, and then we have all of the heat and area just around it that is going to be affected. So air molecules, we're talking about heat given off or taken in. We're talking about all sorts of stuff, but it's just right around our reaction or our system. Now the surroundings in the system will always be stated for you, so that way you can determine what the universe is that they're talking about. So if we take this one step further, we can talk about heat and cold. And if you put two objects together, the one that's very hot and one that's very cold, we're going to have all of our heat transfer from the hot to the cold spontaneously. So again, when we talked a little while ago, we said that an increase in temperature really means that you're increasing the kinetic energy of the particles and how they move around. And so these hot particles are going to want to move. They're going to want to spread out. And these cold particles, now it can only be cold by like a couple degrees or so. I mean, that's still colder. These cold particles, they're just going to want to stay put. They are not moving around as much as these hot ones are. So if we increase the temperature, we increase the kinetic energy, and therefore we increase the entropy. Because these hot particles are moving around, they're spreading out, they're going further and further out, so they are moving and transferring over to the cold. And again, this does happen spontaneously. However, if we try to move the other way, and move any heat at all over from this cold area to the hot area, it's just not gonna happen, folks. So unless we put in some type of energy or system or machine or something else going on with it. So this is an example of your refrigerator and how your refrigerator actually uses Freon to draw out the heat from the inside, making it more cold. So if you were to actually like put your hand in the back of your refrigerator or underneath where the motor is, it'll feel hot because this not spontaneous. It's not going to happen unless we have some sort of energy or machine working with it. So to this, we can say the second law of thermodynamics. All spontaneous processes, therefore, have an increase in energy. So if we are looking at the total entropy of the universe, and again, the universe is both our surroundings and our system together, then if the entropy of the universe is greater than 0, you're going to have a spontaneous reaction. So if you have a positive S, it's going to be spontaneous. If the change is less than 0, so a negative S, it's going to be non-spontaneous. And then if it is 0, that means they're at equilibrium. And in the last video, we said that if it's at equilibrium, it's going to be a reversible process where you can go back and forth between the reactants and the products. Another way to look at this is with fun math. Yay, math. So our surroundings, our entropy of our surroundings is equal to the negative heat reverse over our temperature, and our temperature is in Kelvin, or because we can do a lot of other mathy type stuff, we can say the enthalpy of our system over the temperature, again in Kelvin, is going to be equal to our change in S for our surroundings. So we'll get to this again later on with an example, but I just wanted to throw that out there right now. Wonderful. Let's move on to the third law of thermodynamics. The third law says that the entropy, so that S value we've been talking about, of a pure perfect substance at 0 Kelvin is 0. Awesome. But we have a problem with that. When are we ever at 0 Kelvin? Right now, the absolute temperature or absolute zero isn't possible. Scientists are getting really close, like 0.0001 or something. But we can't reach absolute zero. And at normal room temperature, we are definitely not at absolute zero, nor is anywhere in the world at absolute zero besides in these scientists' laboratories. So for right now, until the world is at absolute zero, which I hope never happens, the entropy of the substance is always going to be positive because of the fact, again, that we are not at absolute zero. If we are at any other temperature, S is going to have a positive value. So what values do we normally use for temperature? In a standard state, a gas normally has a pressure of 1 atmosphere. That's at sea level. So solids and liquids also use 1 atm because that's just our standard pressure. When you did gas laws, we always had our standard temperature and pressure. And so the standard temperature is 25 degrees Celsius or 298 Kelvin. Just like in gas laws, coming up in thermodynamics, when we talk about temperature, we're gonna have to use Kelvin. And you'll see that in just a second. And then whenever you have a solution, we're assuming it's gonna be 1 molar. So molarity will not usually play into the fact unless it's specified otherwise. And we're just not gonna do that. So let's look at an example of this third law. It says, calculate the entropy of the reaction for a balanced chemical equation. And I have this balanced chemical equation here that says we have 2 moles of this dihydrogen sulfide. We have 3 moles of oxygen gas. They're going to react together. It's going to form 2 moles of water vapor and 2 moles of sulfur dioxide gas. We also need some other information in this problem. We need to know what our standard entropy values are. So for this problem, we're assuming we're at 1 atm and we're assuming that we're at 25 degrees Celsius. So we have a whole bunch of standard values, and you would be given these if you need them. And so for our dihydrogen sulfide, our standard entropy is 205.8, oxygen's 205.2, water's 188.8, and sulfur dioxide is 248.2. We also have this handy dandy equation that we can use for our problem. Now it says that for any reaction, the change in entropy, the standard change in entropy for a reaction, it's the sum of your coefficients from a balanced reaction, that's why these moles are super important, times the standard entropy of your product, so that's where these values come in, minus the sum of the standard entropy of your reactants times their coefficients. So the first thing we're going to look at is we're going to look at the products because we want to know the change in entropy for the reaction. So we can use the equation here. For our products, we have 2 moles of water and we have 2 moles of sulfur dioxide. So if we look over here and look for our water, water is 188.8. So I'm going to put 188. Where did it go? So looking at this example, now that I actually have all my numbers here that I can move around, if we look at water, water has 2 moles as its coefficient. So I'm going to put a 2 here. Then I'm going to multiply by the standard entropy for water, which is 188.8. I also have 2 moles of sulfur dioxide, and I'm going to multiply by its standard entropy, which is 248.2. Multiplying these 2 values together gives me 377.6. And multiplying these 2 values together gives me 496.4. Because again, we want to sum, this big E means sum, all of this reaction stuff. Ignore the dog. So when we add them together, we end up with 874 total. So our entropy of our reactants is 874. I'm just going to leave that over there so it's a little bit easier to see. I'm sorry, our products, not our reactants, our products. All right, let's do the other side. So for the other side, we have 2 moles of disulfur or dihydrogen sulfide. So here's my 2. And dihydrogen sulfide is 205.8. So I'm going to multiply 2 times 205.8. My oxygen gas has 3 moles, so I'm going to take my 3. And my oxygen has a standard entropy of 205.2. So I'm going to multiply those 2 numbers together. 2 times 205.8 is 411.6. And 3 times 205.2 is 615.6. For a whopping grand total, when you add them together, of 1,027.2. Let's look back at our equation. So for our equation, we have the sum of our entropies of our products times the number of moles for each one. We calculated that to be 874, and minus the sum of our reactants times their coefficients, which we calculated to be 1027.2. And when you subtract the 2 together, you end up with a whopping grand total of negative 180.2. So what does this all mean? We have a negative S of our reaction. A very long time ago in some video, we said that when we have a negative delta S, it is non-spontaneous. So in order to make this reaction work, it needs energy to drive it. It is an endothermic reaction. It needs energy in order to make this happen spontaneously, because currently it is non-spontaneous. All right, friends, let's do one more example. This one is slightly more involved and slightly different. So now we have 2 nitrogen gases, we have oxygen gas, and we have dinitrogen monoxide. I'm given an enthalpy for this reaction. I'm given all these S values, and I want to know the change in entropy of the surroundings associated with this reaction. So in a moment ago, we calculated the entropy of the reaction, not the surroundings. you are not going to use this information. This information is just extra information that is given us to confuse us in the problem. Why are we not using it? Because we can go back to this. And why can we use this? Because we are given an H value. We are given this enthalpy of the reaction. And because of this, we can calculate our delta S of the surroundings. So let's go ahead and calculate it. First, we have our delta S of our surroundings is equal to negative delta H of our system, or in this case, our system is our reaction. So this could also be our system. They're the same thing in this case. And divide it by the temperature. So first things first, we need this delta H. Guess what? We're given it in the problem. However, this is a positive value. This is a negative sign. So negative 163.2 kilojoules. Uh-oh. Whenever we have entropy, entropy is always in the units joules per Kelvin. This is not joules. This is kilojoules. So in order to change this into joules, we have to multiply it by 1,000. That will give us the amount of joules, or move the decimal 3 spaces to the right. So instead of having all this, now we have negative 163. Move it 3 spaces. So 1 space, 2 space, 3 space. That's the amount of joules. It's hard to do this with just one hand. And then we also need our temperature, but the temperature is in Kelvin. So if we take 25 and we add 273.15, we get 298.15. So that goes on the bottom. Awesome. Now we can actually finish the problem now that we have all of our information. So our final amount is negative 547.37 joules per Kelvin. And remember, this negative sign means that it's non-spontaneous. All right, part B. Yes, there's a part B. Determine the sign of entropy for the change for the system. We're still not using these S values. To find the change for the system, it's even easier, friends. All we're looking at is the amount of moles. That's it. That's all we're doing. So in the reaction above, let's move this up a little bit. We have 2 moles of nitrogen. So our reactants, we have 2 moles of N2. We have 1 mole of O2 for a grand total of 3 moles of our reactants. For our products, we have 2 moles of this dinitrogen monoxide. So 2 moles N2O. If we think back to the previous video, then we know we're going from a lot to a little. When this happens, it's gonna have to become more ordered. More or ordered. And when this happens, we have a negative delta S of the system. We have, because we're just looking at the sign. We don't need a value. We just want the sign. So we could calculate it, but that's a pain. All we're looking for is the sign. So by comparing these moles, we're able to determine that it's going to become more ordered. And so our sign is going to be negative. Part C. Determine the value for the universe. And is it spontaneous? So this goes back to an equation that we used a little while ago. I don't know if I can actually find it in all the stuff that I have over here. Where is it? Oh, here it is. Okay. So delta S of the universe is equal to delta S of our system plus delta S of our surroundings. And again, we're determining the sign, nothing more than that. Well, for our system, we did that in part B. Our sign of our system is negative. So I'm going to put a negative value here. Does it matter what the number is? No, it doesn't, because we're just looking for the sign. So we just need to know the sign of the other two. Now, in part A, we calculated the entropy change, that's S, for the surroundings. And we determined that it was going to be negative. So delta S for the surroundings is also negative. So to calculate S of the universe, we add a negative plus a negative. And when we add two negative values together, we're going to get a negative. So this is the answer to part C. Well, I hope you all have enjoyed these videos. I've enjoyed making them. We will be resuming class on Thursday, and I can't wait to see you all then. Have a great day.